One of the things I liked best about studying maths at university was being introduced to some really weird and wonderful functions. Things like sine of 1 over x, or the indicator function on the rationals. And I'd like to talk about one of my all-time favourite maths problems, which is about trying to come up with a function so weird it's not even obvious at first that it exists at all. The problem is this. Is there a function from the reals to the reals which takes every value on every open interval? I'll explain the terms in a second, and we'll discuss whether such a function exists and how to prove it. Although not to give the game away, but I also give an explicit description of one called Conway's base 13 function at the end. It's a lovely construction, but there's a lot to learn trying to puzzle this out. If you've not seen the problem before and want to go, do pause here. It's well worth thinking about. First though, let's just unpack the statement. An open interval is a block of numbers on the number line. For example, numbers between 1 and 2, not including the endpoints. We're asked to find a function which takes every single real value on every such block. So for example, between 1 and 2, there should be some x such that f of x is equal to 17. And another x which is such that f of x is equal to pi, or the square root of 3, or 10 million. That sounds tricky, but in fact it's not too hard to do for one single interval. Think about the function f of x equals tan x over the interval minus 90 degrees to 90 degrees. We see that every y value has some corresponding x value, and that's exactly the condition that we're looking for. Our problem, though, asks us for this to be the case on any block between any two distinct real numbers. Right, so you can clearly forget about this graph having a gradient anywhere or being continuous anywhere and so on. It's a really odd creature. Our first step is going to be to just turn the problem around a bit. Remember, given an element in the range of a function, say for example 17, we can think about the values in the domain, x values, such that f of x is equal to 17. Now we need that every open interval exactly contains such an x. And put differently, between any two distinct real numbers, there is an x such that f of x is 17. Now, happily, topologists have a name for this kind of set. It's called a dense subset of the reals. And of all the many, many, many dense subsets of the reals, there is one sort of undoubted celebrity, being the rational numbers, Q. So why is that dense? Well, let's pick any interval and pick any number in that interval. Say you're choosing the mean of the endpoints or the geometric mean. We can take the decimal expansion of that number, and if you chop its tail off far enough, so if you go far enough along its decimal expansion, and you chop all the rest of it off, you will eventually get inside the interval and you will have found a rational number which lies inside your interval. Okay, so we can set f of x is, say, 17 if x is rational. That's sort of one real number down. So, how can we deal with all the other real values? Well, we can sort of move the rationals around a bit. For example, if we pick square root of 2, we might want f of the square root of 2 to be 1,000. That's good, but we can also set f of the square root of 2 plus a to be 1,000 for any rational number a. And that won't interfere with my f of any rational number being 17. And we'll have a dense set of stuff going to 1,000. But we're still clearly not going to get all the real numbers by going sort of one at a time through very famous irrational numbers like the square root of 2. Now our next trick is to deal with them all at once. And for that, I'm going to say that two real numbers, x and y, are friends if x minus y is a rational number. Square root of 2 plus 1 and the square root of 2 will be friends. And this definition partitions, like it separates out the real line into friendship groups. And each of those friendship groups is a dense subset of the reals. It's a subset of the kind that we're looking at. So, I claim that we're done, we've solved our problem, if we can match up friendship groups with the real numbers, 1 to 1. So one friendship group, one real number, another friendship group, another real number. Because if we can, then we can just define f of x to be the real number matched to the friendship group. And in fact, if you know a little set theory, this is not hard at all. The basic idea is to describe what's called the cardinality of a set of friendship groups, or equivalence classes. And this is a notion associated with the size of infinite sets, and you can perform some arithmetic with this notion. So in particular, the cardinality of an infinite set is the same as the cardinality of the product of that set with a countable set, which is like if you have the smallest kind of infinite set, something you can match up with the whole numbers. So our claim that you can match up friendship groups with real numbers in fact follows immediately once we can construct a one-to-one function between the product of the rationals and friendship groups with R. And in the spirit of a good textbook, the rest is left as an exercise. So after all that work, we've seen that once we don't have any assumptions about the continuity of a function, and we can end up sort of tearing up the real line in all sorts of horribly complicated ways. And you might have noticed that I did a lot of choosing in that argument, and I relied a lot on what's called the axiom of choice to get out of trouble associated with choosing infinitely many, in fact uncountably infinitely many things all at once to define the functions I was using. And I mentioned before that there's a beautiful example due to Conway which avoids all of these sorts of issues. I just wanted to explain that construction briefly now, and it goes as follows. So if we fix any x in our real line, we're going to think about its expansion, but not its decimal expansion. We're going to think about its expansion in base 13. So this uses digits 0 to 9, as usual, as well as a, b, and c. And we're going to define f of x based on 3 cases. So if that base 13 expansion of x ends a, x1, x2 up to xn, where those xi are all numbers between 0 and 9, then a c, then y1, y2, blah, 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 where all those yi's are also numbers between 0 and 9. Then we're going to send x, so f of x is going to be the decimal, now the decimal, not base 13, x1, x2 up to xn, point y1, y2, blah, 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 blah. So case 2, maybe not so surprising now, if x ends b, x1 up to xn, where those are numbers from 0 to 9 again, c, y1, y2, blah, 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 then we're going to send f of x to minus x1, x2 up to xn, point y1, y2, blah, 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 blah. In our third case, we just send x to 0 if we're not in either of the previous 2 cases. Now the proof that that works, I think I'm going to leave as another exercise, but I'd recommend sort of thinking about taking a real number, its base 13 expansion, and just noting that you can modify the tail, if you like, the base 13 tail, and if you do it far enough down, you can change the size of that number by as small an amount as you'd like, but still be able to hit any real number. Okay, so I think I'll leave it there. Thank you very much for watching, and I hope you enjoyed.